So yeah, today I'm Mahidhar Tatineni. I lead the user services group here at SDSC, and I'm going to talk about code migration today. Uh, just a bit about Complex. I think you might have all seen it. It's an SDSC program to basically provide training that covers like non-programming skills to effectively use computing resources and broad range of topics, and it's supported by the NSF award number there. Uh, so a quick outline of our uh, uh, webinar today. Basically, I'm going to talk about the code migration aspects, basically with Expanse in mind, but this can be a more general approach that you can do on most machines because most of the big HPC centers have similar setups. So the outline is going to basically looking at it. We'll start with applications that are already available on systems. So typically they are available via modules, or some of them might be in Singularity containers. I'll give you examples of that. Then we'll particularly look at Python and R-based applications because this is one major source of questions on our end, and there are several ways of getting these installed and used. So I'm just going to go over those, and then move on to essentially building applications from source code. This is not that common, but we do have users who build everything from a source code. So we can give you an example of that. And also, I'll talk about SPAC, which is a approach to basically build packages from source, but for custom environments. And then lastly, I'll just talk about user-built containers and how you can use Singularity or Docker images. So starting off, let's get going with basically applications that are already available. So this is specific to Expanse, but as I said, most HPC centers would have a large suite of libraries and applications that are already on Expanse. And this can include even commercial packages if we have the licensing cost covered. So for example, on Expanse, we have QChem, Abacus, and Gaussian as the commercial packages. And the primary approach is we make all of these available through environment modules. So you can use the module spider command to find applications that are already available via modules. And some of these applications are complicated to install through the regular install process that we use. So we end up doing a containerized approach. Examples are like PyTorch, TensorFlow, AlphaFold, and so on. So those we make available through containers, and there are a few that are maintained and updated by SDSC staff. So I'm going to point those out. As I mentioned, yeah, this is Expanse specific today, but I think similar things are available on other clusters, including the Triton Shared Computing Cluster at UCSD. And then one last note there is basically all of what I'm talking today is typical for a on-premises slum or basically directly installed cluster. But we do run a few Kubernetes-based clusters at SDSC, for example, Voyager and Nautilus PNRP. There, pretty much the entire environment is in a container, and you can essentially use Docker images. And we do have an environment to build those images if needed, but essentially the approach on an on-prem cluster like Expanse will be very different from a Kubernetes setup where everything is containerized. So just wanted to point that out. So how do you find applications? So let's start off with an example of basically MATLAB, for example. If you're trying to look for all the MATLAB installs on Expanse, you can do module spider MATLAB. And you can see it shows up various versions, 2020B, 22A, 22B, and so on. And if you want, you can actually do a spider on the specific version to get more details. Uh, for example, if you do module spider MATLAB 2022B, it's going to give you all the versions that are available there. Now, you might be wondering why there are two versions. The reason is on Expanse, we actually have different hardware on the GPU node versus the CPU nodes in terms of the CPUs themselves. So bulk of the cluster in the CPU section of only section of the cluster is actually AMD ROM processors, and on the other one we have uh, Intel processors on the GPU nodes. So we separated the two stacks out because of compatibility reasons. So that's why there are two different things. And if you actually pick one of those particular versions, so out of the two, I basically picked the first one there, that with the hash LEFE for OQ. So if I do like a module spider on that, it actually will give you all the details of how you can load that. So you can see you can load the CPU module first and then load the MATLAB. So this essentially is going down the CPU tree of our module tree, essentially. And if you actually do this with packages that have multiple options, you'll actually see them too. So like, for example, if you do module spider FFTW, we have different versions, the 215 and 338. We also have possible matches that are uh, uh, providing the same library but are customized. So for example, the AMD FFTW that is showing up here. So it's good to check and make sure whatever you pick is compatible with the rest of your environment. As I said, if you do a spider, it'll actually tell you the details on a particular package. So yeah, in this case, if I pick the FFT3310 with CSM hashtag there, then you just see that it's actually built based on the CPU stack with the GCC compilers and then the MVAPish to MPI library. So you can imagine if you're trying to build up application from source, and you have dependencies on MPI and you have dependencies on other libraries. You need to make sure that all of them are combined with the same compiler and MPI, for example. So like say you need FFTW and you need like an IO library like HDF5, you need to make sure that you're loading the same stack for both of them so that they're compatible. So that is uh, how it all works. So now, once you know, okay, I need to load these particular modules before I can load the particular library that I need, you can go ahead and do that and actually see what gets set when you load these modules. So for example, here, I picked one of the FFTW libraries and loaded all the dependent modules and the FFTW library. And if you do a module show, it actually tells you what it's doing when you load that module. So first thing you know is it's got a description of what is there. Uh, but then you also see that it sets a bunch of paths. Then this is essentially what's happening when you're using modules, right? It sets the library paths. It sets the path for the binaries. So for example, and all of these are being prepended, so it doesn't clobber what you already have existing. It just adds more directory paths to the existing path, basically. So all that means is if you have a binary associated with the package that you loaded, it would show up in your default path. Just as a caution, the CPU and GPU stacks are completely independent. Don't mix the two, as I mentioned earlier. Uh, the reason is this, right? The features that are on the AMD CPUs are different from the ones on the Intel CPUs. For example, the Intel processors support AVX 512, and if something gets built with the AVX 512 optimization, it won't work on the AMD side because the AMD ROM processor we have only supports AVX 256 or AVX2 basically. So you need to be really careful about loading the modules. So make sure all of the modules that you load are consistent with the node that you're planning to use it for those. So on Expanse, that means if you're on the GPU nodes, if you're trying to run a code on the GPU nodes, make sure you go down the GPU branch of the modules. And we do provide examples for a lot of our applications in CM shared examples SDSC on Expanse. So you can go and actually look at how to run some of these codes. And I have a snapshot of the listing there, and you can see some of the standard applications that we have examples for, like AlphaFold, Amber, which is a molecular dynamics package, and Neuron, which is a neuroscience package, and so on. So there's lots of options that you can look at. So that's the first level of things, right? Where we've already installed everything, we've got modules for you, and we have mechanisms so you can discover what's already installed in modules. And then you go look at the examples, make sure you load the right combination for the right nodes that you're using. And then you just run. You don't really have to do any installations. There's no real code migration because we've done the installs for you. So there's nothing that you need to change as such. And you can just run as is using our binaries. Now, the next step is, okay, we couldn't make these work in our standard modules. You can also use applications via Singularity containers. And on Expanse, the containers are in CM shared apps container Singularity. And we've got a few standard applications that are available via Singularity, like TensorFlow, PyTorch, AlphaFold, ParaView, which is a visualization software, and Visit, which is also visualization software. We also have the extreme scale scientific software stack, which is the E4S stack in a container. And I have a link there for the E4S stack. But basically, this has a lot of very optimized installs for a lot of math libraries that are used at in large scale codes like Trillionos or PETSI or and so on. And the reason we have this container is because this is this whole stack is essentially managed for the exascale computing project, and it's actually uh, kept updated and also has the right combinations of these libraries that can work together. And this is important because a lot of the math libraries, there are version compatibility things that you need to keep in mind. So if someone has done the homework and given you a compatible set, it's best to use those. I think that's where a container like this will be pretty useful. And I should say that this E4S container has both uh, uh, non-MPI and MPI, so builds of these applications and libraries. So you should be able to use them multi-node if needed. And for all our containers, the ones that we maintain, we actually make the container definition files available, and Marty has it on his GitHub site, and I have the link down there. And this is one thing to keep in mind. If you're using our container as is, there's not much you need to think about. But if you want to add to what we have, like say, for example, we have a TensorFlow container and you actually need some more Python packages or some extra stuff that you want to add to it. It's best to take our definition file as a starting point and then add or layer what you need on top of that. And the reason is for a lot of packages, we make sure that the drivers that are on the system are compatible with what's in the container. So, and vice versa. Basically, we make sure whatever we install is compatible with the drivers on the system. So, so that means you if you layer on top of it, you'll be guaranteed that it's going to run fine on the system. And this is important to keep in mind. Even later, I'm going to talk about it even when we do the conda install aspects of it. Because if you go pick the latest container, for example, from Docker Hub or some other place, and just pull down the latest version of TensorFlow and latest version of CUDA and everything, and our driver doesn't support it, you're going to have failures. So you need to make sure whatever you do is compatible with our drivers. So that's why we have these definition files as a starting point. Now, how do you actually use applications through the containers? So we have examples, as I mentioned, but I'm just showing you one of the PyTorch examples here. So for the Slurm part of things, which is where you request the resources from the cluster that you need to run your job. So in this case, we're saying I need one node, I need 10 CPU cores, I need 90 gigabytes of memory and one GPU. And this is pretty standard, right? This is how you would request resources from Slurm. Uh, so that part is very standard. The only thing on the application side is instead of now loading the modules for that we have installed, you reset everything, just load the Singularity module that puts Singularity in your path, and then everything runs through the container. So in this case, I'm executing using the PyTorch container that is in the shared directory that I had mentioned before. Few things to keep in mind. If you're using containers, you need to also make sure if you need any data from the directories that are on Expanse, you need to bind them in. So by default, the home directory gets bound to the container, but anything else, like say Lustre or the local Scratch directory, you need to do the explicit binding. So just make sure you do that. So in this example, for Expanse, I'm doing /expanse and /scratch. Now, /scratch is the NVMe storage that's on each compute or GPU node, and /expanse is where Lustre is mounted. So it's enough if you got both of those paths, and that should cover everything that you need. And you might be wondering what this dash dash NV flag is. That just pulls in all the NVIDIA drivers correctly into the container. After that, it's just your regular Python script that you want to run that can be there. And this all runs in the Singularity environment. So remember that anything you need should be in that container and not outside, because if you install something in your home directory and try to use it, uh, it's okay if it's compatible with the environment in the container, but if you say load some modules and then install something in your home directory and then use the container and try to use it with that particular install, it's going to fail because the environments won't match. So you need to keep that in mind. So all of those were packages that are already existing on Expanse, either through modules or through containers that we manage. Now comes the next part where you find out that, hey, whatever is on Expanse or any other system is not something that I can use. Then what do you do? Now, I've split that up into two things, Python and R. Now, for each of these, there are also module-based installs. So I'll show you those, but I'm going to more talk about the Miniforge, conda installs, and the Singularity approaches. So first things, as I said, we already have some things available via modules. So for example, NumPy, SciPy, and so on. So for those, you can do what I was showing you earlier. Just uh, uh, module spider and module show. I'm going to take a brief look at the questions. So I see there's a question about whether you can change the Slurm file. Yeah, you can actually change those numbers to what you need. That was just an example. So So you can do a module spider and module show to get more information. Some of these modules will be dependent on MPI, so be careful. Uh, and if further installs are needed, actually now I'm going to switch this mini conda to mini forge. I think I missed this in my slide, but I think if I in the next slide you'll see we are going to do mini forge or singularity approaches if something that we don't support is needed. And this happens often with Python and R. So where we have installed some packages, but uh, in most of the Python and R applications, they're changing quickly. People are coming up with new versions, new packages, and we don't have them in our modules. And typically, in those cases, we are not going to go ahead and change the system-wide install, mainly because uh, there are dependency issues. If we try to satisfy everyone's Python requirements, it's almost impossible, I think, to get everyone's requirements into the same distro. So that is when we basically recommend doing conda installs. And for conda installs, we are suggesting doing mini forge as the starting point. And this is basically it's going to set the channel for all the packages as conda forge. And you can use mini conda installs with other channels, but if you're doing that, please do look at the licensing terms because I think things have changed recently. And some things are like, for example, the default channel with mini conda 3 uh, has restrictions on what can be used without payment. So you should check that out if you're going to do mini conda 3 installs. Otherwise, I think you can just basically start with the mini forge conda installer. That will set your channel to conda forge, which is all the free packages. And a lot of the packages that you need will be already in the conda forge distro, so you should be fine, I think. Now, things to keep in mind if you're doing conda installs, don't put this in a Lustre file system. This is because the conda installs create lots of very small files, and that can cause system-wide problems if you try to load them from a lot of different nodes at the same time. Because what essentially happens is you might have 50,000 small files, and if that's in a Lustre directory, and you try to load it from say 10 nodes, you're essentially causing 5 million, I mean 500K, like 500,000 requests all at the same time. And that doesn't do very well on the parallel file system. You can put it in the home directory, or we also have examples where you can actually just install this into the local Scratch dynamically and manage them. And if you need to go that route, we can help you with that also. One other thing to keep in mind with conda installs, and this kind of ties into what I had mentioned earlier. Uh, 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 it ties into essentially the versions of the drivers and on Expanse. So for example, our current driver version on Expanse GPU nodes is 5.15.85.12, which supports basically CUDA version 12. Now, if you go in there and try to install like something CUDA 13, uh, Conda will just install it, or you'll get an installation done, but then it's not going to work because the driver doesn't support it. So that's the reason you need to be careful. Uh, so, um, so that's basically all the packages that you can install via Conda. You can basically do that, and I have some example in the next uh, couple of slides on how to do that. So one thing is when you're doing installs, it's best to install it on a compute or GPU node, just so that you can quickly test if whatever you installed is compatible with the particular node. For example, if you're doing a GPU install and you're on a GPU node, you can quickly check if whatever you installed still works fine, right? Like the driver versions and all that are compatible. The other is we have limits on the login nodes and on the memory and on the number of cores. So that causes problems too with some of the installs, especially if you install R packages. R decides to use, if you pull in one of the math libraries that R is using, and that will automatically detect the number of cores on a node and try to use all of them, which on a login node is a problem because it causes issues with the R limits. So, so basically, keep that in mind when you're installing. And also, one other thing to keep in mind is at the end of an install, Conda will ask if you want to update your bash RC into your uh, 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 update your bash RC to basically have the initialization in it. It's best to avoid that and do the initialization setup in your run scripts instead, because otherwise, every time you log in, it's going to try to go walk through the entire um, conda tree again, which is fine. It's going to work, but it'll be just make your command slower and everything slower. So in this snapshot, what I'm showing you is essentially asking for one node. I just went on a CPU node in this example. I basically did a wget on the Miniforge installer script. And once the script is there, I just do sh and run that script. And that will walk you through the installation process. So when you first start, it's going to show you a license agreement, and you can read it and say yes to it. And then you can install packages. So I'm here showing you how to install, like, say, a CUDA toolkit. So you can do a conda search and CUDA on the CUDA toolkit, and it'll give you the list. And as I mentioned, just keep in mind, whatever you install, make sure it's compatible with our driver. So here I'm installing 11.8.0, which is clearly below the limit that we support. So because 12.0 is supported with our driver, so you can actually go ahead and install that. So I'm just saying yes to that, and it downloads and installs that package. So, and then you can do a conda list to see what all packages are already there, and you can update if you need something else. So that's the conda-based installs of Python packages or CUDA or R. You can do all of them using conda. And that's what we have been suggesting for a lot of our Python users, is to use a conda-based install in your home directory, and then you can customize it with environments to exactly what you need and so on. Now, the MPI for Pi is one thing to keep in mind. This is the Python implementation of MPI. Now here it's important that it's consistent with the MPI being used underlying, right? So we do have a system installed pi-MPI for Pi module. And I show you the two examples here, one with Intel MPI and one with MBAP H2. Now, remember, if you use these, then you have to make sure that all the packages you need are under our system install modules. If you don't, then you will probably end up doing a conda install. But if you just do a conda install of MPI for Pi, it will just do the conda-based MPI install directly. So it will not use the system MPI. Now, this is totally fine if you're running within a single node, because you will end up getting the MPI just running within, like launching all the tasks in a node. The network is not involved, so there's no real optimization worry using it. And remember, a single node on Expanse has 128 cores, so you can go up to 128 MPI tasks and not have an issue with this setup. Now, the risk is when you go multi-node, and the conda-based MPI install usually pulls in an open MPI install. So the multi-node will work, except it's gonna not know about our InfiniBand performance network. It will end up using Ethernet for the communication, which will work, but is not ideal because that's a much slower network. It's also not designed for user traffic. On Expanse, we are using it for, system management tasks and so on. So that's not a good place to send your intensive I/O or user communication traffic. So that if you need a multi-node install, unfortunately, right now the only way is to combine it with a system installed MPI. The only risk with this is if the system-based MPI is also pulling in another compiler that is inconsistent with what's in the conda, you might see some problems. But that's the way to go, is you'll have to pull in an MPI on the system level and then do a conda install of MPI for Pi from source. So you would download the MPI for Pi source and then do a conda install. And when you do that, it will actually sorry, not a conda install. You'll install the Python package from source, but in your conda environment. So what that would do is it will detect the MPI automatically and then use the right one. And that will give you the high performance network capability. Again, as I said, don't go down this route unless you really have to. And because that involves a little bit of a careful combination of installs. So let me see how we are doing on time. We're actually in pretty good shape with time. So let me see if there are any questions. Okay. Yeah, I think Marty's answered the question in the chat, so I'm going to continue. Yeah. So next come R-based applications. So this is, again, we have some R applications and modules available through our regular modules environment. So you can do module spider R dash to find all of them. So for example, we have BioBase and do parallel and ggplot2, and all of these are in our own modules. And if these installed versions are enough for you, you can just go ahead and use that. You don't need to go install it again. But if you end up finding out that, hey, that particular R package either doesn't exist, like I want some particular thing and it like Swerat or something like that, and you don't see it, or you say that, oh, you have BioBase, but it's too old a version, I need a newer version. I think in that case, it's best not to try and use our environment and just go do a conda install. So again, you can do a Miniforge install as I showed you before, and then just get the R packages from the conda forge channel. Again, keep in mind, you cannot mix the R apps from the modules that we have with the ones from the conda installs. They will conflict and fail. So here's an example of R. So that's one way of doing things. The other is we can actually do a Singularity approach. So here is an example of R that I'm running through Singularity. So this is actually a question that had come in from a particular user. So this is a real example. So they were looking for an R package called excerpt, and it turns out that there was a Docker image for it that already existed. So then what we did is get an interactive node. Again, this is for the same reason I was talking about. There are limits on the login nodes that will cause issues if you try to build things. So I got onto an interactive node. I think in this case, it was a debug node. I export my temporary directory variable to the local scratch. This is something to keep in mind in general on Expanse, is that r/temp is very small even on the compute nodes. So make sure you redirect your temp directory to the NVMe scratch location. So I do that in the first line here, then load the Singularity module, and then I'm going to take that Docker image and build a Singularity image. So we don't support Docker natively on Expanse, but fortunately, you can build Singularity images from an existing Docker image. So that's what I'm doing here. So I'm doing a Singularity build and just giving it the name of the image, and then pointing it to the Docker image of excerpt as the source. So when you do that, it's going to create a bunch of, uh, I mean, it'll start building the image and it'll download a bunch of the blobs with the parts of the uh, 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 Docker image, and then put together the Singularity image. So once this is done, you will have an image called excerpt.sif, and then you can do exactly what we did with the PyTorch container when we were using Singularity, and just use R through that. So that's uh, an easy thing. If you already have a Docker image, this is what I would suggest. Don't even think about doing the mini conda part or the mini forge part, because uh, everything is self-contained and you can just run that image. But you can do a conda install, as I mentioned. So here I'm showing you how I was searching for versions of R. So I did a conda search, r-base, and I was looking for all versions 4 and above. So I just did a 4-star, and then you can see all the versions that you see. And I think they have all the way to 4.4, the base versions of R. So you can install the one you need. Um, so uh, so going back to the Singularity example, I can once I have the image, this is how this Slurm script is going to look. So in this one, R typically uses compute resources. So I'm basically doing partition equals shared because we don't use all 128 cores in these examples. So we are just using shared. One node, one task per node, and CPUs per task is 8. And remember, number of nodes and number of tasks, the combination of these will give you essentially the total number of tasks that you're launching. And then each task can then do threads. So I'm saying, hey, I have only one task, but it'll have 8 threads. That's what this essentially means. But these are requests. So remember, this just goes to the scheduler and asks for requests. So when your job runs, these are the resources it will get. Your code or your run script still needs to use those effectively. So nothing will happen automatically is what I'm trying to get at. So in this case, I was doing this because I know the excerpt code under the covers can do threading for the math functions, and then can use the cores. So I'm using 8 cores and 16 gigabytes of memory, and similar thing as before, reset, do the Singularity Pro. So this basically ensures that we are not pulling in any of our own modules other than the Singularity one. And then I do Singularity run, bind in the input directories. In this example, actually, we are binding it into specific locations on the container. And this is because the container runtime expects the inputs to be on a particular path, the outputs to be on a particular path. And then it also expects the reference data sets to be in certain locations. So that's what's happening here. So they're all kind of being laid out correctly for the container. And this is the container that I just built using the Singularity build command. So remember that this container build only needs to happen once. So if you're running this multiple times, just keep that container in your home directory or in your Lustre directory, and then just use it, reuse it, because the container itself doesn't change. Only these inputs and outputs will change, but those are being bound in from Expanse, so that's fine. So so basically, now so far we have gone through cases where modules are already there on Expanse, and you can just use them as is. We have example files for these. We have looked at containers that already exist on Expanse. That's fine. We looked at Python installs and R installs where we can use all three approaches. That is, you can have modules, you can have a mini Forge Conda install, or you can have a Singularity approach. But that's not the only types of codes that run on Expanse or any of our HPC systems. Sometimes people will want to build applications from source code. So this usually means that you're building from source code, but you might still use some of the libraries that are already installed on Expanse. And this is what I'll go over next. So if you have installed from source, typically there either will be configure script or make file. So here I'm giving you an example for a code called Quantum Espresso, which has a configure script. And what a configure script essentially does is detects what's in the environment and uses the paths automatically. So in this particular case, I'm basically setting up a compile environment. So I'm basically saying, hey, I need the CPU stack, I need GCC 9.20, OpenMPI, and some AMD libraries like the Bliss library, which is the equivalent of a LibPack math libraries, and libflame uh, and FFTW. So that's kind of setting up the environment. But then the configure script actually needs some arguments. Now, one thing I want to stress is that this is very particular to Quantum Espresso, right? So different configure scripts will be looking for different variables. Although there are some things that are standard, like C flags and CXX flags. Those are pretty standard across all configures. But there might be some other environment variables that a particular software will need. So you should set those accordingly. So in this case, I'm setting all the compilers to the GNU compilers, setting the flags that are specific to the machine. So I'm saying O3 optimization, and the architecture is Core AVX2. And this is because our CPU nodes that support AVX2. And then the Quantum Espresso configure script also looks for locations of FFT. So I'm setting those. Now notice here, I'm actually setting the path based on variable AMD FFTW home. And this, if you go back to our FFTW slide, and maybe I can actually go there and show you. I might be going too far back, but oh, it's actually not here. Okay, we actually set this in our module. So that's the thing to remember. So otherwise, we would have to give the full path to the location, but we actually set some of these variables in our module. So when you do a module show FFTW, it will tell you what paths are being set. So you have to set those. And the configure script also is looking for BLAS and libpack locations, so we give them all those things. And then you run the configure script, and in Quantum Espresso's case, it will go create a make file. And then you can just run the make to compile it. Now that's one way of pointing to existing libraries. So the one thing to remember is if I go back here to this slide, all these compile environment things are something that's already installed on Expanse. So we actually have also a Quantum Espresso module, but sometimes people come back and say, oh, but I need a new version or something like that. But so all these are already installed. These are dependencies that are needed for the Quantum Espresso install. So we are going and pointing all the dependencies out, locations out to the configure script and running it. Sometimes you don't have a configure script, you just have a make file. So that's another example. So in those cases, you have to manually point all those locations out in the configure script. Sorry, in the make file. So you can see in this is an example of a make file where the compiler is defined, where the lib flags and include flags are defined. So that's where I'm going and putting the Expanse specific locations now. So these are again things that are already installed on Expanse, like the BLAS, Open BLAS, and the FFTW. But now I'm pointing it out in the make file for my own software, right? So I'm saying, hey, if you're looking for um, FFTW include location. So often these libraries will have include files that define things like the functions and the any custom variables and so on. And they will also have library files that you need to link in. So those are the two typical things that you set in your make file. So that's what I'm doing here. And then you run your make file, it's going to find what's already installed and then build software. So those are installs from source. Going back to some things to keep in mind, I've mentioned some of these, but I want to say it again. When you're installing from source, make sure all the compiles are compatible with the node that you're going to use it on. So for example, if you're going to run on the GPU node, do the compilation on a GPU node too. Don't just compile on the login node and then try to run it on the GPU node. It's most likely going to fail. And as I said, don't mix installs between the GPU and CPU stacks. Uh, and the compiles done on login nodes will most likely fail on a GPU node. So if you see that, like if you see, say you compiled like a code on the login node and you tried running it on a GPU node and you get a segmentation fault, most likely it's because the processor incompatibility. So now the CPU codes you can combine on the login node because the processor is the same as our CPU nodes on the login node. So the only thing to keep in mind is if your compile needs a lot of memory, which happens sometimes, right? You end up needing 15 gigabytes of memory because the compiler optimization is trying to do too many things and it uses a lot of memory. Then it's going to fail. And if that happens again, solution is to just get interactive access to a compute node and compile there. Remember, your home directory and your Lustre directory are mounted everywhere. So it doesn't really matter where you compile, and as long as the binaries or the source are in the home directory, you should be able to see it everywhere. So what I mean is you don't have to basically recompile it for the like on a different node. They're going to end up in the same location. The one other thing is the math libraries. Typically, there are several options. So you can actually look around and see what works best for your application. So like, for example, if you're looking for the BLAS libraries, math libraries, there's OpenBLAS. There's one that's compiled from source from the NetLib source. There are Intel math kernel libraries. There are the AMD libraries, the AOCL libraries. They all work. They all will link in fine. Uh, Performance really depends on your particular uh, functions that you're using and so on. So this is something you should test and make sure. Like for example, there are cases where the Intel MKL library works better on the AMD nodes than the OpenBLAS or AOCL. Uh, uh, it's just optimized better for the particular function you're using, for example. The other thing to keep in mind is these libraries are in all non-standard locations. So if you go back here and look in my include flags, you can see it's in CM shared apps, SPAC, CPU, op, blah, 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 Linux, GCC 10.2, and with this whole hash and everything there. That's not where typical installers will look for things, right? Like, so for example, if you're following along compile directions from some online help guide for a particular package, and it says, oh yeah, it should be in user include. Well, it's not going to be in user include. So it's going to be in whatever that whole path is an include. So you have to change your options to point your build scripts to the right locations. And the other thing that often happens is in those online guides, they will say, oh, Lepak is not installed, just do sudo yum install Lepak. That's not going to work either. A, because you don't have sudo, and B, we really can't afford to give sudo to users on a shared system. So that's not going to be allowed either way. So you have to basically build in locations that you can write to, install in locations you can write to. And if you have uh, uh, lo packages installed in non-standard locations, you just need to change your build scripts to point to them and not just try to install it in the root directory, essentially. Um, so that's that. And then one last caveat, the Intel compilers will work fine on AMD nodes. As I said, sometimes they're faster. So that's all fine, but don't use the -x host option if you're using Intel compilers. This is because the Intel compiler doesn't detect the AMD ROM processor correctly, and then it'll end up being really slow because it optimizes for some very generic CPU instead of like an AVX2 supported CPU. So for that, this is again going back to you may be following along, like say a WRF build script from somewhere that says, oh yeah, just use Intel compilers and use X host. That's not going to work very well. So if you see something like that, just switch it to the core AVX2 flag that I've listed here. And again, this is just for the Intel compilers. All right, so that is using libraries that we already installed, and then we already, and you're just using those dependencies that are already installed in modules and then building from source your own code or some other code. There are also mechanisms to do the whole install from source, including the dependencies. So SPAC is a package manager that lets you do these sort of things easily on HPC systems. So we actually, all our software installs are done through SPAC, and we actually have a GitHub repo with, that Marty is set up and all of us contribute to for machine-specific installs. And so you can look at those because we have actually submit scripts that will go ahead and install things. But the only thing to keep in mind is obviously you can't write to our SPAC location, so you will have to write everything to your home directory. And actually, AMD provides recipes to install things, and they've actually made them public, so you can go look at them. So here I'm showing you one example of installing the WASP code from source, including all the dependencies. So if you look at what I'm doing, I'm basically setting up the SPAC distribution, creating an environment so that you can replicate this later if needed pretty easily. And I'm saying, hey, install AOC C libraries, install the OpenMPI library, install OpenMPI is the MPI implementation. And then I just do a SPAC install with a bunch of dependencies, and everything gets built from source for, optimized for Expanse in your home directory, and then it all lands in your home directory. And then you can use the binaries from your home directory. This is all fine. One thing to keep in mind is when we are doing the MPI, OpenMPI install, we are actually using some of the system locations for the Luster and for Slurm and RDMA packages and so on. And this is important because if you don't do this, it's going to install all of it from source also. And if that's incompatible with our drivers, you're going to see problems. So you should have those as external dependencies. Again, this is a little bit for an expert user. If you do end up in a situation where you need to do this, contact us on the support ticket, and then we can follow up and try to help you out. But I just have this example as just to let you know that, hey, you don't have to use anything that we have installed and start from scratch and just use all the libraries from scratch, build them all from scratch. And sometimes that might be the case because the libraries that we have installed for dependencies aren't the right versions or need some other additional flags enabled, so on. That can happen, right? Or yeah, you have a very new setup that isn't compatible with the libraries we have. All of those reasons you may want to do everything from scratch. So this is fine. So almost done. So we have looked at now building everything from source. You can also build containers yourself. And this is, again, if it turns out sometimes even the SPAC-based install doesn't quite work in the regular Expanse environment because there are some other packages that are needed that are not in SPAC. And then you can't install those easily, and it needs just a lot of customization. In those cases, you just go into the Expanse environment and into a container environment and do it. for basically your code porting purposes. So for MPI, so the things to keep in mind if you're doing Singularity containers is if you're doing MPI based install, the MPI should match the external MPI version of that's already installed. Make sure the InfiniBand drivers are in the container if you're doing that. Again, as I said, we have the sample definition file, so use those as a starting point. Same thing for GPU installs. You need those drivers to be compatible as well. Now, the other issue with building these is if you're building from definition files, you need root access, so you cannot do this on Expanse directly. So you have to build elsewhere. Most of the time, your laptop or desktop might be enough to build like a Singularity image. But if it gets too big and you don't have the resources, you can use a cloud resource. And if under access, Jetstream 2 is a good option, and we've used that quite a few times ourselves. Just an example of a definition file. This is one of Marty's examples that's there. You can see it sets up the base image for basically the base CentOS version that you're using. So here it's CentOS 7.9 in this example. And then does a bunch of yum installs within that. And then if you look down here, we are actually configuring and installing MVAPIsh within the container. So concluding, there are several different options to get applications working on Expanse to port your code. First one and the easiest one is see if it's already there. Don't try to replicate something that's already there. Look at our examples directory and see what works. For R and Python, see if it's in modules. Most likely, the ones we have are not as up to date, so you would end up with conda installs. So as I mentioned, go the Miniforge route. Or you can use containers. Both are valid options. Only thing to keep in mind is you cannot mix all of these together. So if you go conda route, you need to keep the conda consistent all through. If you go the Singularity route, keep it in all in Singularity images, or at least in the same environment if you're building something. If you're building from source, we saw you can use the libraries and compilers that we have already installed, or you can go do everything from scratch. You can use Docker images via Singularity on Expanse, TSCC, and most HPC clusters. Or you can build your own definition files. And last thing is there are clusters where everything is containerized, where none of the first options that we mentioned apply. You just go straight to containers. But we do have development environments on those clusters to actually build your own container. So that's where I will stop. I think I'm a few minutes over, but let's stop and see if you have any questions.